So in this video, I'm going to start talking about isomers. Isomers is a topic that we're going to come back to quite a bit this semester, but this is just going to kind of be a quick introduction to them. So be really careful. We have a lot of I's. We have isotopes, ions, isomers. So what isomers are there molecules that have the same molecular formula. So if you remember from the previous video, that's where we just say how many of each type of atom we have, right? So C3H8. So atoms that have the same molecular formula but different structures. If you were to draw them out, they're different, even though they have the same number of each type of atom. So these have the same molecular formula, but different structures. I'm going to modify this. I'm going to say, but are different. Because there's a different type of isomers that we're going to talk about this semester. So have the same molecular formula, but are different. I know that's really vague. How they're different is going to depend on what type of isomer we have. So the ones that I'm going to talk about now are going to be structural isomers. So these are going to have different structures, but we're going to have isomers that only differ on their orientation in three-dimensional space. They're mirror images of each other. We have an entire chapter on, they're called stereoisomers, on stereoisomers. So structural. Also called constitutional isomers. So just one type of isomer. Like I said, we're going to have more than one type of isomer this semester. So structural or constitutional isomers, these have the same molecular formula because they're isomers, but different structures. So same molecular formula, but different structural or condensed or skeletal formulas. Once we learn to start naming organic molecules, they're going to have different names. They're just going to be different boiling points, different melting points. They're just plain not the same thing, even though they have the same number of each type of atom. So the first example, we'll do the C5H12. So I'm going to draw skeletal structures. So my first option here, I have 5 carbons, and I can just draw them all in a straight line. So the way that we would do that is we will zigzag this guy. So just since we're still learning, I have a carbon here, a carbon here, carbon here, carbon here, and carbon here. So that gives me my 5 carbon. And then if you go and count the hydrogens, right, I'd have 3 here to get my 8 valency electrons. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It'd be quicker to just erase that guy. So let's redraw it. So that's my option, right? I could just take, what I did is I took all 5 of those carbons and we just bonded them in a row, and then I put the hydrogens on them. Remember, hydrogens can't go in the middle. Another option, I could do 4 carbons in a row, right? And then I could put one of those carbons on one of the other carbons. If I go and stick my hydrogens on there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So same thing, it would have its 12 hydrogen. I don't want you to think that you can draw lines for hydrogens. You actually would have to put the H there. Otherwise, it's actually a CH3 group, right? If I go and look at this, it's a line. It's not a hydrogen. It's a CH3 group. So I'm erasing it. Right, so that would be my second option. Be careful. If I was to draw 4 in a row and put it on this carbon, it's the same thing as this one I just drew. It's just flipped front to back and upside down, right? It's the same thing. It'd be like, right, if I took that one and put it there, it's the same thing. It's not different. These are not isomers of each other, right? They are the same molecule. Remember, isomers have to be different, right? I have 4 carbons, right? 4 carbons with a branch on the second carbon. 4 carbons with a branch on the second carbon. We're just counting from the opposite direction. So do be careful for that. I do have one more possibility though. We could have done 3 carbons in a row, and then I could put a carbon, right, 2 carbons on that central carbon. So the way we would draw that using skeletal structures is in that manner. So these are my options, right? These are my 3 structural isomers. Be really careful. If I ask you to draw all possible isomers and then you draw something that's not an isomer, then I'm going to mark it wrong, right? These are my only 3 options. You could draw them differently. Like if I was to do 5 carbons in a row, but for some reason I wanted to do this instead, it's still just 5 in a row. It's just bent, right? It's not an isomer. It's just a different orientation. It's not different, right? It'd be like, it's easier if you could see me, but my arm, right, is attached to my body through my shoulder sort of thing. And if I was to stick my arm straight out, it's still attached in the same orientation. If I was to put my arm up in the air, it's still attached in the same orientation. It's just oriented differently, right? The attachment point hasn't changed. So that's kind of what this and this are to each other. The only way to make an isomer of it, this is kind of gross, but I have to actually cut off my arm and then attach it to some other body part of mine, right? I would actually have to move it to a different location, not just orient it differently. So watch out for that. A lot of times I'll get people that just draw the same thing oriented differently, right? Remember, these 2 are not isomers, right? One's just upside down and then mirror image of the other. So be careful. If I was to do, going back to this one, right? If I was to do 3 in a row, and then I decide to put a chain of 2 on here, well now, be careful, this one is the same as those 2, right? It's a chain of 4 with a branch on the second carbon, but again, this part here is just bent. So sometimes you have to draw something wrong before you notice that it's wrong. So when you're drawing these, it's really easy to draw something that's not an isomer at first, but then just really go back and look at it. Be very critical and then just cross out anything that's not correct. I only have 3 isomers for C5H12. You could draw them slightly different, but there should only be 3 unique answers. One more example. Let's do C3H8O. So this one, I'm going to get a couple possibilities, and we'll start just doing it structural because you're still learning. I could do all 3 carbons and then put an oxygen on the end, right? If I did all 3 carbons, and I know the hydrogens are missing, but we'll come back, and put the oxygen on this end, it's the same as the first one that I just drew. So this gets crossed out. That's not an isomer. I could do 3 carbons and put the oxygen in the middle. So that's a possibility. If I would do 3 carbons, put the oxygen in the middle, but it's pointed down, it's not an isomer of this one, right? They're the same thing, just flipped upside down. I could do a carbon and oxygen. Oxygens can go in the middle, hydrogens can't, but there's nothing that says oxygens can't. And then my 2 carbons, that would be fine. Do not do this, however, because that is the same as the one that I just drew, right? But backwards. And then if I was to go and put all my hydrogens on there, it does all add up to the right number. So I'm going to do lines again, but I'm going to erase these. So I would have 1, 2, 3, 4, 5, 6, 7. And then there is one on here, right? It doesn't have a formal charge with its 2 lone pairs. So that makes 8. 1, 2, 3, 4, 5, 6, 7. One on here, so 8. 1, 2, 3, 4, 5, 6, 7, 8. 2 lone pairs, right? Hydrogen has its 2 bonds. So drawing these skeletal structures, that's this one, right? I have 3 carbons in a row. 1, 2, 3, and then my OH group. I could do this one, that's this one, and then this guy. So these would all be isomers of this. All of those oxygens do have 2 lone pairs. So again, same molecular formula, but they're actually different. And then how are these different? These ones, because they're structural isomers, have different structures, right? If we were to draw them out, they draw out differently.